Thank you. Oh, hello. Welcome back, everyone, to another Learning Glass video. Today, we'll talk about the first law of thermodynamics. And we started off using the first law of thermodynamics for closed systems based on the energy level of your system in terms of internal energy. Today, we'll also summarize how that is handled for an open system or a system with chemical reactions. In those cases, it's better, more convenient, more efficient to keep track of the energy level of your system by using enthalpy. So, for a closed system, you care about something where there's no mass coming in or out. You want to analyze the energy levels and the interaction through heat and work transfer. So a closed system, and there's no chemical reactions, where when there is chemical reactions, there's more ways that the energy levels can be affected. And in this case, you use internal energy. Under these conditions, you use internal energy U. So there's different ways for the energy level of your system to change. You can have a kinetic energy due to some change in speeds. You can have potential energy due to some change in position in the force field. But in thermofluids and mechanical engineering, the most unique thing that is one of the most powerful things is internal energy, which is the microscopic energy. And the way what helped us to get a lot of new technologies was to get a really high temperature, like from burning things or getting nuclear energy. To get a real high temperature, that translated, or that high, the temperatures was like a tangible parameter that we can measure, but what it's really happening is that the internal energy increased. And then we can use the first law to engineer and design and or understand fundamental processes and more useful applications as well. So for the first law, ignoring kinetic energy and ignoring potential energy effects, we can still do a lot of very useful and important applications and phenomena using this form of the first law of thermodynamics. So what focus on today as well is how do you find internal energy. So there's a lot of engineering and physics into how do you find heat transfer. That's a subject of a whole class, and there's a lot we can talk about, but we'll focus on internal energy. Same thing with work. We do talk about that mechanical work a lot in class, and different models we can apply to evaluate mechanical work. But today we'll focus on internal energy. So one way to do it is that the most accurate way is to find a table so that you can just simply evaluate delta U equals U2 minus U1, the final energy minus the initial energy. And just find a good table for the specific material you're interested in, like water. And when you're working with water, we commonly have liquid, vapor, or a mixture, and that's a part of the process of determining these energy values. But when you're looking at a table, those are accounting for everything that just give you this value that would be useful in the first law. But you can also use the concept of heat capacity. There's two different types of heat capacity, one for internal energy and one for enthalpy. And heat capacity is useful because it gives you a parameter that depends on the material, and it gives you an equation rather than a tabulating. Rather than having to look things up, you can have a continuous function to do this energy balance using equations rather than having to look it up. So that's where that's how heat capacity is useful, and it's a different way of evaluating internal energy. So the heat capacity, the CV one, which changes with temperature, gives you internal energy. So if you were to integrate from some initial temperature to a final temperature, this function of CV over this interval of temperatures, that will give you the internal energy for any process. Doesn't matter if the volume changes or not, you'll still get the same answer as long as you use the right temperature endpoints. And often you can find this in terms of a polynomial. So for a given material, you can find CV as a function of T equals A plus BT. For example, this is a common form. You might find other, where this function, polynomial in this case, gives you a relationship on how heat capacity changes with temperature. And when you integrate that, it will give you a relatively accurate way of finding internal energy. So that's what heat capacity is used for. It's used to find internal energy change when you're using CV. And heat capacity doesn't have a direct connection to heat. It has a direct connection to internal energy. In some cases, it is heat transfer, but in all cases, for any process, it gives you directly internal energy. So this actually, CV should actually be called internal energy coefficient. And there's different levels of accuracy. So again, the most accurate will be just to read off from a table into this equation. But in most engineering, you want to set up an equation or a code, a computational code. And when you're using a computational code to solve these through an algorithm or through some different parameters scenarios, that's where heat capacity becomes useful. So for a given material, for a given system, you'd want to find an accurate function that captures the temperature dependence of heat capacity. Polynomials are often used. There's a famous thing called, in thermal fluids, rocket science, called NASA polynomials. And it's literally something like this with more terms. And for a given material, or like literally each molecule or each atom you're working with in your system, you would define these heat capacities and then relate it to internal energy and then integrate it over the temperature range of interest, or use that in the formulation to find the temperature of the final temperature. So for the least accurate way, which we have done and which is nice for simple calculations, least accurate would be to say that delta where instead of having this integral of a polynomial function, you would simply say that if this CV was constant, it did not depend on temperature, this integral becomes simply T2 minus T1, and that is least accurate because you're not accounting for this temperature effect. And you can do this for cold air, for example, which we have done and will do in class. At 300 Kelvin, or some other temperature, or you can say CV average equals CVT2 plus CVT1 over 2, some average value where it's constant. So I'm running out of space here, but this would be if the CV value no longer changes with temperature, this integral becomes simpler. You could just say delta U equals CV dt. On the cold air standard, when evaluating these reciprocating engines, Otto cycle and diesel cycle, we often use this simplification, which is a pretty rough estimate because the engines, they get very hot, but we ignore that effect. Or if you wanted to be a little more accurate, you can say that if you know the temperature at the end, you know the temperature at the beginning, you can pick some middle ground. It'll still be constant, but you can just take the average. Okay, so this is how you would use the first law. You would use internal energy in the first law if you had a closed system with no chemical reactions. This is the most useful way to use the first law of thermodynamics. Okay, so let's contrast that with another case which occurs a lot in engineering and science and physics, is if you were to have an open system, meaning that there's flow coming in and out, or if you had a chemical reacting system. So if there's chemical reactions causing the molecules at the beginning of the process to undergo a reaction to change to another different molecules, then the energy levels at the beginning and at the end would be affected by the chemical bonds that change. And both of those cases, either of those cases and or both, you would use enthalpy to account for internal energy. So it's related to internal energy, but this extra PV term accounts for a lot of things conveniently. So this can account for flow, going in and out of the system. It can account for chemical bonds. And it's not that it accounts for chemical bonds directly, but it accounts for the fact that during a chemical reaction, you often have changes of pressure and volume. And with that, the enthalpy captures it much easier, and the reference point based on enthalpy is much better to work with when you have these change in chemical bonds. So the first law in that case would be delta H equals Q minus W. It's still the first law. You're just using enthalpy to account for this flow effects or these chemical bonds effects. Then, similarly, the most accurate way to find enthalpy change would be to say simply delta H equals H2 minus H1, where we'd use from tables like we have done in steam tables, air tables, and refrigerant tables. And this is a whole process which we have done for steam, and depending on the assumptions you make, like the ideal gas air tables, all you need is temperature. But that's a simpler case. For steam tables, you need both temperature and pressure, or two independent properties to pin down where you look in the table. It's not as simple as only temperature. You need two properties to pin down where you are on the tables. So depending on the situation, you can find this from tables, but there is some practice and concepts involved with properly finding the right enthalpy at the state you are at. And then when you do that, that will be the most accurate because these tables consider everything. But if you want to use an equation and parameterize this internal energy in an equation rather than relying on a table, which is more accurate for computer codes, as I was saying before, what you can use heat capacity. And heat capacity is used to find internal energy, and it can be used to find enthalpy. That's what the difference is between these two heat capacities we have, Cp and Cv. Cv is for internal energy, Cp is for enthalpy. And both change with temperature. The higher the temperature you go, the more heat capacity these molecules have. The problem is that name is unfortunate because heat capacity is not directly depend on heat. It depends on, it gives you enthalpy. It's most directly related to enthalpy in Cp, most directly related to internal energy for Cv. Doesn't have to do anything with heat. It always has to do something for any process with either enthalpy for Cp or internal energy for Cv. So for any process, you can say delta H is the integral of Cp dt, even if the pressure changes. For any process, you can say delta U equals the integral of Cv dt for any process. And if you can capture this temperature dependence and then integrate it over the temperature range, it'll be relatively accurate. Depending on how detailed this equation is, you can meet the accuracy of the tables. So for a given material, Cp as a function of T equals, it's different. Let's say E plus Ft plus Gt squared plus Ht, for example, for a given material. So if you had a certain system, like NASA does it, each atom and each molecule, they found these polynomials to give you a way to find enthalpy using this equation. And for each, it changes for each material. It's the response of the material to a temperature change. That's what Cp is and Cv is. It's a response of the energy to temperature change. Doesn't have to be heat. It's only about a temperature change of the system. Each molecule responds differently. That's captured by Cv and Cp. And then Cp gives you enthalpy change, Cv gives you internal energy change. Doesn't have to do directly with heat, doesn't have to do directly with pressure or volume. It's just temperature response to enthalpy or temperature response to internal energy. The names are unfortunate, they're just historical and they've always stuck. This is the most general definition of these. And they're useful because you can use these equations to find enthalpy change. If you need to find enthalpy change, you can also use a table if you use the right methods, which is a skill in itself. And again, for constant, the least accurate way to evaluate this is to assume that you have a constant Cp. When you do that, you can say delta H equals Cp delta T. And that's an easier equation to use. And sometimes it's relatively accurate if you have a small, if you use the value of 300 and the temperature change is very close to 300, it's only like 320 minus 300, this will be pretty accurate. But if you have a big temperature difference, it becomes less accurate. So you can use it in the case of cold air at 300 Kelvin. That's one common use of this assumption. Or you can find some another random value depending on your problem, or you can define some Cp average. Some temperature condition, and then average with the second temperature condition, just to have some constant value. So it's the least accurate, but it can become relatively accurate if you have a small temperature difference. You don't have to do this integral, and if you know the Cp, you can use it rather than a table. But if you, like in this engines, we use it in the cold air assumption, even though the engine goes to a very hot temperature due to the burning of the fuel, we still use it because we can get some nice equations to capture the physics, even though that equation is the biggest, one of the big reasons why that equations of the cold air standard are inaccurate, because you pick of heat capacity at 300 Kelvin and the temperature goes much higher than 300 Kelvin, and that changes the heat capacity significantly, so it becomes less accurate. So these are all ways to use the first law. So this is still the first law here. This is still the first law here. The difference is, depending on the situation, using internal energy to capture the energy levels is more convenient. In these cases, using the enthalpy to capture the energy levels is more convenient. And then CPs will give you delta H, CV will give you delta U. And that's the energy levels of your system. The energy levels of your system, in what the usefulness of the first law is that you care about and you define this system, and the energy levels can change due to these interactions with the surroundings. These interactions could be in the form of heat transfer or mechanical force over a distance, work. And in this thermodynamics class, we do spend a lot of time evaluating this work component for the mechanical force, and many times we can get a nice equation based on pressures and volumes. So it's always going to be related to a pressure change and a volume change, but when you have an ideal gas, you can get more explicit equations for this work transfer depending on the conditions, whether it can be constant temperature, constant pressure, constant volume, or no heat transfer. Those are other scenarios which we will save for another video. Okay, so with that, just wanted to show why we use internal energy sometimes and why we use enthalpy sometimes. You can use these interchangeably. It just takes more practice to keep track of everything properly. But a good way to go is just to remember that for a closed system with no chemical reactions, that's why you see delta U used. and you see enthalpy used in other times to account for flow and chemical bond changes. Okay, so with that, I'll see you next time. Thank you.